Hello class, welcome back to lecture 2. Today we're talking about the algebra of sets. So basically we're going to be talking about different ways you can put sets together. So we should think about this sort of how we think about numbers. So there are operations that we use to combine sets or manipulate sets, and they obey some rules, just like for numbers. We have operations like times and plus, which we can stick together under some rules. So for example, we have the distributive property, which says that we can do something like this. The the multiplication distributes into the addition, and we get something like this. So that's a rule that multiplication and addition obey when you combine them. So we're going to do similar things today with sets, but first we need some operations that are very much like multiplication and addition are for numbers. Okay, so here's the first operation. So we need two sets, so we can stick them together. So we'll call them A and B. Then there is another set. So the notation for this new set that we create, well, since it's an operation, we think about it as an operation, we sort of stick it between the two things that we're putting together, like we would a multiplication between numbers. So this is like a capital U. It's called a union or a cup. So this is called the union of A and B. So what is it? So of course, when they teach you about multiplication and addition, they teach you the notation, but they also teach you like what it does. So what does this do? So it's going to be a set. So it's got elements in it. So what are the elements? It consists of elements from both A, let me just say from A and B actually. Meaning you just take everything in A, you take everything in B, and you put it all together in one big set. And so people often, if you want to be very precise about it, this is the actual set theory definition. You would say something like this. It's the set of all X. So X is just representing any element. But what do I know about them? It's the ones that are in A or in B. Either is fine. But we'll do examples to see how this is a bit simpler than the definition makes it out to be. It's really just saying all the stuff in A, all the stuff in B, put them all together. That's the union. So then sort of the opposite of that is called the intersection, which is what this symbol means. It's like an upside down union. So the set A intersect B is how you can read this, is called the intersection of A and B. And it has elements. So the way you get A intersect B is you take everything that is in common to both A and B. So it has elements, the ones in both. They have to be in both A and B. So the very fancy definition is written like this. So it's all the stuff, all the elements that are in A and in B at the same time. So we write it like this. Okay, so you take A, you take B, and you look at what's in common to both. that's what's in the intersection. It has to be in both. While the union, either one is fine. If it's in either one, then it's in the union. But to be in the intersection, it has to be in both. Okay, so then one more operation that we'll be dealing with is the complement. So if we have a sample space, so for the complement to make sense, you need some sort of outer space that you're working within. These other two, you don't really need that. So I didn't have to mention a sample space. You can just talk about them independently of a sample space. But here we really need a sample space. If we have a sample space and A is an event, so that really means, again, from last time, it's a subset of omega. Well, then what's going to often happen is there'll be stuff that's not in A that you want to reference. So that's what the complement is. So then A, and what we do is we put like a C as like the exponent. This is called the complement of A. And its elements, so it's still a set, are the ones not in A. So it's sort of like the opposite of A. It's sort of like a negative. So in set theory notation, we would write something like this. It's the X's that are, you still got to be in omega. You got to live in this bigger space, this bigger set, the sample space. But it's the stuff that's not in A. So you would write it like this. Okay, so we'll just see some examples. We're not going to deal with the strict definitions too much. So let's just play around with this with some examples to get used to this stuff. Okay, so let's think about a dice roll. So we just have our 6 outcomes. Oops, almost forgot 5. We have our 6 outcomes. And then let's just have some events. So one of them might be, oops, let's do this, 2, 4, 6. And B would be, let's do like 2 and 3. So then let's do some of these operations. So what would A union B be? Well, you got to be a little bit careful. So it's all the stuff that's in either A or in B. So you just go through and you say, what's in there? Well, it's got a 2, but there's not going to be 2 2s just because you see it twice. You don't count repeats. Just the fact that it's in one of them is already enough. The fact that it's in both has doesn't help us at all for the union. We don't need it to be there twice. You just write it once. So there's a 2 in there. There's a 3 in there. There's a 4 because of A, and there's a 6 because of A. So that's the union. We just take everything in both and put it all together. So being in either one is fine. The intersection is, now we look at what's in common to both, and there's just that 2. 2 is the only thing in both, so that's why it's in the intersection. What about the complements? So the complement of A, so what's in omega that's not in A is 1, 3, and 5. So that's going to be the complement of A, because those are what's not in A. And we can also do B complement. So what's in B is 2 and 3. So what's not in B is 1, 4, 5, and 6. So that's what's going to be in B complement. So everything not in B, that's what's in B complement. So this is all just pure set theory stuff. But in our language and in the context of this class, meaning we're going to use the word events or outcomes instead of subsets and elements, we could sort of think about these like that too. So the intersection consists of outcomes in both A and B in the events both A and B, but you can also think about it like in terms of occurring. So like, when does this occur? Well, it only occurs if both A and B occur. So you run the experiment and the outcome that happens needs to be in both A and B for the intersection to occur. Meanwhile, the union consists of outcomes in either one. Either one is fine. And then when does this thing occur? Well, it occurs if either A or B occurs. Because either one of them occurring means that the outcome was in at least one of them. So therefore the outcome is in the union, because that's how unions work. In fact, we could also use our other types of wording and language. So we can say things like this. A intersect B, that's always going to be a subset of A, because A intersect B is smaller. It has all the stuff in A, but only the ones that are also in common to B. So we could say that A intersect B implies A, to use that other language from last lecture, and that's because an outcome in here occurring means an outcome in A occurred. Because it's a subset. But you can go a little bit further. You can then say that A is inside the union, because the union is bigger. It just expands upon whatever A is and adds more stuff to it from B. So then you could say A implies the union for the same reason. You could do the same thing with B. So A intersect B is a subset of B, because you're just taking B and taking less of it, only the stuff that's also in A. And then when you take the union, you're making it bigger because you're adding the stuff that's in A. So unioning sort of seems like addition-ish. So you can sort of think about it like that. Okay, so it's good to compare numbers, but not too closely, because when we view these as operations, we actually get different rules. So viewing intersections, unions, complements as operations gives some interesting rules. And so it's similar to the number rules. So operations for numbers. So here's one. If I want, I can take an intersection of a union. So I could say, what's B union C? And then I could intersect that with A after. And the intersection actually distributes. So this is a distributive property. Just like multiplication distributes over addition. So you can do A intersect B and A intersect C independently, and then union them together after, and you get the same thing. So it works just like for numbers. 3 times 2 plus 4 is 3 times 2 plus 3 times 4. So that behaves just like multiplication and addition do, but the opposite for numbers doesn't work. So for example, I cannot do addition over multiplication. So this is not equal to 3 plus 2, 3 plus 4, and then multiplying. So that's not true. So it only works one way. Multiplication distributes over addition, but addition does not distribute over multiplication. But the cool thing about sets and unions and intersections is it does work the other way. So it's a little bit different, than for numbers. So if I switch these from what I did up here, I did intersect and then union. Now it does work. Still works. So I could union them independently and then intersect the result. So they distribute both ways. They distribute over each other. And then a couple more is sort of how do negatives work? Well, that's sort of going to be similar to how complements work, but it's a bit different. So if I take a union and then I complement, it's not just going to distribute. So you might hope that you get this, but actually you don't. And instead, what happens is it turns the union into an intersection. So it sort of flips it over like that. And then the opposite is also true. So this flips that way. So these are just four rules. This one, this one, this one, and this one. These are 4 rules. There's many more. And in a set theory class, you would painstakingly go through them and prove them all. But we're not really going to do that because it's not a proof class. It's not a set theory class. So in a proof class, we would prove these. Very typical. But for us, we're just gonna say, okay, it's fine to sort of just show the idea visually. And what we're going to do is we're going to use Venn diagrams to do that. So here's how Venn diagrams work. If you have a sample space, and you have 2 events, we can draw the possible operations pretty nicely by just drawing the 2 sets as bubbles inside of the sample space omega. So the idea is that this rectangle is omega, so it has all the outcomes. And then these bubbles are inside of it, so they are subsets. And so they just have some of the outcomes. And the ones that they have are the ones inside of the bubbles. So then we can shade regions corresponding to the results of the operations. Okay, so first example, if I want to know visually what the intersection of A and B is, I can just shade it right here. So it's the stuff in both bubbles. And so that's just this stuff, because in red is what is in common to both A, that's what's in A, and this is what's in B. So the only part that's both red, or sorry, that's both green and blue is this red portion in the middle that I've shaded. So that's this part. Okay, so that's the intersection. Visually, you can also visualize the union pretty well. So what's the union going to be? Well, now I just shade everything in both, and that's the union. So sort of like this extra, this whole big thing. It's everything. I can also visualize the complements. So I don't really need two sets if I'm just doing the complement of one thing. So if that's A, then what's A complement? It's just everything not in A. So it's all this stuff shaded. So it's all that. And then B complement would look the same basically. So those are how we can visualize the operations that we learned. So then to check the rules that I put up earlier, it's not really a big step from there. We just draw the situations. So for example, let's check this rule and see how it looks visually and see if it makes sense visually. So this is saying that if I union two things and then I complement it, it's going to be the same as if I intersect the complements individually. So on the left here, what does this look like? Well, now I have two sets, so I got to draw both of them. And the complement of the union, so this is the union. And now I'm just going to complement it, which I'll do in green, which means I want to shade everything that's not in there. So that's going to be all this stuff in green here. Okay, so is that the same as this other picture where I do A complement and B complement, and then I intersect? Well, let's see. So this is A and B. So let's do A complement first, which would be, I'll do it in red here. So this will be A complement. Okay, and then B complement. Would be, I guess I'll do it in white here. So this is B complement. So then I'm intersecting them. So I just want to shade the stuff that's in common to both. And yes, it is going to be the same as the green stuff. So let me actually do the same color, sorry. So just to be very careful. So if I overlay the red and the white, and then I say, let me have them doing sort of crisscrossing so it's easier to see. And then if I say, what part is both red and white? Well, it's just this same as the green area that I drew before. So it's just this stuff out there. Okay, so visually we can see that, yes, this equation makes sense. And just to be extra careful, when we're saying something like this, when we're saying that two sets are equal, this really means that they have the same elements in both sets. The exact same elements. So if there's a 10 in here, then there's a 10 in here. If there's a 12 in here, then there's a 12 in here. They have the exact same thing in both sets. Okay, so if we wanted to check the other rules, we could. It's just sort of unnecessary. It'll take a long time. So especially the ones with 3 events. So with 3 events, you would need to draw a third bubble. So you would actually need to draw something like this. and shade appropriately. So you would get things like, this is A, B, and C. This part is like B intersect C, and so on like that. It'll take a while, but you can check the rules using this type of diagram. And then it turns out if you wanted 4 or more, it becomes a lot harder to draw, and you have to not use circles. You have to use other shapes to get all the possible intersections and stuff. So it's sort of cool, but I'm not gonna worry about it too much. Okay, so one more thing we can do is display subsets. So for example, if A is inside of B is inside of C, we could draw that. How would that look? Well, that would just mean that we have A as a bubble has to be completely contained inside the bubble B, which has to then be completely contained in the bubble C. So that's something else we could consider. So remember that this also means A happening event implies B happening, implies C happening or occurring. And visually, it sort of makes sense. If the outcome of the experiment was in A, so that outcome in there happened, well, guess what? It's in B too, so B also occurred. And that's also in C, so C also occurred. So the intuition of the picture helps you make sense of that definition of occurs and implies. Okay, so then one more interesting picture is, what about when you have 2 events and they don't intersect at all? So we haven't discussed that as a possibility yet when we talked about events, but it certainly can happen. And so this is how you would draw it, but what's really going on here? Okay, so an important situation is when events have no outcomes in common, just what's happening up there, e.g., in other words, no intersection at all. Well, how can we denote this? Well, mathematicians have a very special symbol that they use for this situation. So if they want to say that there's nothing there, what they do is they write this symbol, and this is called the empty set. And it's the set with no elements in it at all. So it has nothing in there. And so when you write this, you're saying that the intersection is the empty set because there's nothing in the intersection, which is exactly what this picture is drawing. There's nothing in common. There's nothing in the intersection. So when this happens, the events are called disjoint or mutually exclusive. So I'll be using both of these words pretty often interchangeably. They mean the same thing. It just means, again, that there's nothing in the intersection. There's nothing in common between the sets. So one thing to note is that it's impossible for mutually exclusive or disjoint events to both occur, right? Because if one occurred, that means the outcome that happened from the experiment was in that set. And since the other set has nothing in common with it, there's no way that an outcome in the other set occurred. So that event did not occur. Okay. So let's see an example of this, something like this. So a dice roll for our sample space. And here's two sets that are going to be disjoint. A is that, B is this. So if A is this and B is this, then their intersection is completely empty of anything because they have nothing in common. So they are disjoint. One interesting thing to notice is that by definition, we can always say that if you do A intersect A complement, that is always going to be the empty set because by definition, the complement has what A doesn't have. They're opposites of each other. So it doesn't matter what example you're working in or anything like that. It's always going to be the empty set. So it's just because A complement has elements that A does not. Has only elements that A does not. So they have nothing in common. Another important situation that'll come up when we talk about probability is that events with one outcome only are disjoint from each other. This will always be true. So for example, with the dice roll still, the outcome 1 as an event, so the event with just one outcome, then rolling a 1, and the event where you just roll a 2, those have nothing in common. Rolling a 1 and rolling a 3 have nothing in common. Oops. And so on like that. None of the single outcome events have anything in common. So if you want to say a whole bunch of stuff is disjoint from each other, you can also say that instead of having to list out every single one like I was about to do there. So let's write that as a definition. So when you have a bunch of sets, you can't just use letters. You can't just say A, B, C, D, E, wherever you want to, however far you want to go. We need to use indices. So we're going to say A1, A2, up to AN. So if these are your events or your sets more generally, and you want to say that they are all disjoint from each other, they have no common intersection between any pair, what you can do is you can say AI intersect AJ to mean you're just picking any pair. That's empty. So those two have no elements in common for all I not equal to J. So as long as you don't pick the same number, because of course A2 intersect A2 is just A2. So that's not the empty set. But as long as you pick two different numbers like 2 and 3 or 2 and 7, and you get the empty set, then we say the sets A1 to AN are all disjoint or mutually exclusive from each other. So they have to be pairwise disjoint is another way to say it. Pairwise disjoint, the intersection of every pair has to be the empty set for you to be able to say that they're all mutually exclusive from each other or all disjoint from each other. And that's because it is a little bit different from saying something like this. You can't just say this. You can't just say that is empty. That's not enough, actually. So you can do an example where this is not empty. Well, one of them implies the other, but I don't want to think about it right now. It's on my head, but they're not the same. Okay, I don't want to get it wrong, so I don't want to do the wrong way. Okay, so maybe I'll make that an example. Lecture problems, or maybe not. All right. So one more example for the experiment of rolling a dice, which will help us learn about probability later. So like I said, the events where you only have one outcome in each event. So the event with a 1, the event with a 2, the event with a 3, the event with a 4, the event with a 5, and the event with a 6 are all mutually disjoint. And this will happen for any sample space. If you just take each individual outcome and you put it in its own subset, you make those be events, they will all be mutually disjoint. And also, they represent the whole sample space if you glue it back together. If you use the union and you union all of these back together, you get the whole sample space back. So it might not seem like a very crazy idea or interesting property, but what it'll help us do is think about probability later. So this will help us determine probabilities of events from their smaller parts. So for example, if you want to roll a dice and you want to ask about probability, you might say, what's the probability? So we'll be doing this next time, of event A happening, where A is rolling a 1, 4, or 5. So get the probability of this occurring, say it like that. And what we can do is we can know the probabilities of the individual outcomes occurring. So we want to, by knowing the probabilities of this guy occurring, or this one occurring, or this one occurring individually. So the fact that this happens, which is that you can break up the sample space into events where each event has one outcome, will help us calculate probabilities of bigger events like this by knowing the probabilities of the smaller events like this. So that's for next time when we actually finally talk about probability. But until then, see you later.